So there are two other topics of utility to us in this chapter. One of them is polarity. The other is bond energy, sometimes referred to as bond enthalpy. Now, in the first, we're going to talk about what it means to be a polar or a non-polar bond. And the difference is in the sharing of electrons. Now, in covalent bonds, we know that the electrons are shared between the two atoms. And how that looks is basically those electrons in that bond are moving. And sometimes they're associated with the electron cloud of the one atom. Sometimes they're associated with the electron cloud of the other. Sometimes they're both moving around kind of between them. When we have even sharing of those electrons, where the two electrons generally spend equal time around each atom, we call that a nonpolar bond. Nonpolar bonds, truly nonpolar bonds, are relatively rare. Because especially if we have any kind of heteronuclear bond, where we've got different elements on each side, chances are pretty good that there's not going to be an even sharing of those electrons. And when we have uneven sharing, that is the basis of a polar bond. So polar bonds are by far more common. But the ability to form a polar bond, the ability to attract electrons to oneself in that bond, comes down to a property known as electronegativity. Electronegativity can tell us whether we have even sharing and even charge distribution. So in these temperature maps, we are showing the evenness or unevenness of sharing. The hotter the colors are, the more the electrons spend their time in that area. The cooler the colors are, the more time that the electron is away from that area. And so we can see that in a chlorine to chlorine bond, where we've got a homonuclear bond, same element on each side, we can see that the overall temperature map here shows relatively even sharing. Yes, there are some cooler patches on the ends, but again, that kind of makes sense, right? If I've got a bond between two atoms, the majority of the time, the electron is going to be between the two atoms, not off the one side or the other. In a polar bond, like a hydrogen-chlorine bond here, we're going to see that there is an uneven charge distribution. The side that has the hydrogen with the lower electronegativity is cooler than the side with the chlorine that has the higher electronegativity, which has a warmer color. And this is in complete contrast to an ionic bond, where we see that it's not even a sharing of electrons anymore. That electron is flat out gone. The sodium gave it to the chlorine, or the chlorine took it from the sodium, however you want to look at it. The electron is here and not here. Now, up until this point, we've talked about electronegativity in a very qualitative sense. We've looked at it from a standpoint of position on the periodic table, or a general kind of property that we've been calling non-metallic nature or metallic nature. The more non-metallic something is, the more electronegative it is. The closer it is to fluorine, the more electronegative it is. That's how we've been talking about electronegativity so far. But there is a quantitative way of doing it. It's something called the Pauling electronegativity scale. And if we look at an element on the Pauling scale, what we can evaluate is quantitatively how well does that atom attract electrons? The higher the value is, the more it is likely to do that. And so using the Pauling scale, we can establish relationships between two atoms and say, okay, if I've got this atom and this atom coming together to make a bond, what kind of bond is it going to be? Well, if I evaluate its electronegativity on the Pauling scale for fluorine and compare that to the electronegativity for boron, I can see the relationship between them. We use some general characteristics. This delta chi term refers to the difference in the Pauling electronegativities for the two atoms that make up the bond. If the electronegativity difference is 0.4 or below, we tend to think of that bond as nonpolar. Why 0.4? Well, that's the difference between carbon and hydrogen bonds are generally considered to be nonpolar bonds. So that's kind of the upper limit of nonpolar nature. On the flip side, if the electronegativity difference is greater than 2, we don't really consider that bond to be covalent. We consider it to be more of an ionic interaction. The electron's been stripped away from the one atom and given to the other. In that zone in between, we have polar covalent. So we've got covalent bonds with uneven sharing of electrons. The more great the difference is, the more uneven those electrons are shared. One thing I want you to understand about this scale, though, especially in this domain right here, these are all shades of gray differences. The difference between nonpolar and polar, the difference between polar and ionic, they're shades of gray. It's not a stark difference. If I have a 2.1 electronegativity difference, yes, according to this scale, that would be an ionic compound. But if I look at it spectroscopically and I find that there are covalent bonds that exist between them, I shouldn't be too surprised. These are guidelines. These are not hard and fast rules. There is some variability. There is some shades of gray in between the numbers here. So don't take these as absolutes because they're really not. The numbers that we picked here are generally good, but not always completely do we adhere to them completely. This is the Pauling scale. Now, what we see in the Pauling scale is exactly what we were talking about when we thought about them from a qualitative standpoint. As we go down a group for metals, we say that metallic character tends to increase. So the metallic nature of our alkali metals increases, our alkaline earth metals increases, and not surprisingly, their electronegativities go down as they become more and more metallic. On the non-metal side, we do see a general trend upward as we go up a column, where substances that are more non-metallic, like your nitrogen, oxygen, fluorine, like your halogens, tend to have higher electronegativity values. The last topic that we want to talk about in this chapter are the relationships between bond length, bond strength, and bond energy. Now, if you go back to the beginning of the chapter, we talked about the idea of lattice energy and how lattice energy for ionic compounds is based upon two ideas: charge of the ions, charge generally leading to attraction. The higher the charge is, the greater the attraction. And radius, bond distance. The closer they are, the more attracted they are to each other. The further apart they are, the less attracted to each other they are. Those two same principles show up here in covalent compounds as well. We just call them slightly different things. So instead of charge, because there are no charges in covalent compounds or in covalent bonds, we look instead at bond order. How many electrons are being shared? The more electrons that are being shared, the more attracted the atoms are to each other. After all, a covalent bond is the attraction between the shared electrons and the nucleus of the atoms that are sandwiching them, essentially. The more electrons I put in the middle, the more attractions are going to be present. So a triple bond is going to be more attractive than a double bond. A double bond is going to be more attractive than a single bond. Bond length is handled in a similar way to what we talked about with radius. Bond length, the further apart the atoms are from each other, the easier that bond is going to be to break. The closer they are to each other, the more difficult it's going to be to pull them apart. Well, there's a relationship between all of these. There's a relationship between bond order and bond length. And it kind of is intuitive if you've been following along with the arguments all the way through. If they're more attracted to each other, they're going to be closer to each other. So as my bond order increases, as I go from single to double to triple bonds, I'm going to see my bond go from bigger to smallest. From a bond energy standpoint, bond energy is the energy that's required to break up a mole of bonds. It's dependent upon a number of things, structure being one of them. But the thing that we can look at also is that the more close our bonds are to each other, the more closely our atoms are to each other, the greater their bond order is, the more difficult it is to break it apart, the more energy it's going to take. Now, all of these can be summarized in a chart just like this one. So this is table 4.7 out of a different textbook. In your textbook, I do believe it is table 4.6. The idea in either case is the same. We can evaluate and compare a couple of different scenarios. So let's look at bond order versus bond length and bond strength. We can see that as we go from single to double to triple bond, two things happen. The bond length decreases as our bond order increases, and our bond energy goes up as we go from one to the next to the next. Okay, no real surprises there. Let's do another comparison. Let's compare sizes. If I'm comparing carbon to fluorine versus carbon to chlorine, the only difference in the atom isn't in the bond order, but in the size of the atom that the carbon is attached to. Fluorine is, according to our atomic trend, smaller than chlorine is. Chlorine has the extra energy level. It's going to be bigger. As a result, we see a bigger bond length and a smaller bond energy. So these three concepts, bond order, bond length, and bond energy, are all intimately tied to one another. And the trend that we talked about tends to hold regardless of what it is that we are examining in this particular domain.
One of the things that we can do is we can use this information to figure out what the actual energy, the enthalpy of our reaction. So how much heat is transferred in our chemical reaction. We can actually estimate this using bond energies. And the way that we can do that is if we evaluate all of the bonds that are there in our reactants, and we compare that to all the bonds that are there in our product, we can compare the two against each other, and through that comparison say, okay, the bonds in the products have more energy. That energy had to come from somewhere. It must have come from the outside. So the overall energy is positive, which is an endothermic reaction. Or conversely, we can say, hey, the products have less energy than the reactants did, and so they must have released that energy as the reaction proceeded. That's an exothermic process. So what we really get into here is through the bond energies, we can estimate delta H. And the conventions that we've talked about as far as our sign are concerned apply here as well. Breaking bonds requires an input of energy. Input of energy is a positive energy. Breaking or forming bonds is going to release energy. The release of energy comes off as a negative energy. And so when our total reaction has a negative energy, that means that energy has been released from the reaction. We call that an exothermic reaction. When energy has to be brought in to allow the reaction to occur, energy input is positive. That's an endothermic reaction. And so we can calculate this using this equation. And the equation here is that delta H, the enthalpy of reaction, is equal to the sum of all of the bonds that are broken in the reactants and subtract from that all of the bonds that are formed in the products. So what does this have to do with Lewis structures and molecule drawing? Well, in order to know what kinds of bonds are being broken and what kinds of bonds are being formed, we have to know what the molecular structure looks like. And so if we have a reaction like this, we can use it to figure out our bond enthalpy, or excuse me, we can use our table and our structures here to figure out the actual enthalpy of the reaction. So what I like to do in problems like this is I kind of start drawing lines. So here are my reactants. So these would be the bonds broken. And over here are my products. These are the bonds that form. And so I can start doing an accounting of what's there. I have one nitrogen to nitrogen triple bond. And I have 3 hydrogen to hydrogen single bonds. On the product side, I'm making 2 ammonias. Each ammonia has 1, 2, 3 nitrogen to hydrogen single bonds. So on this side, I have 6 nitrogen to hydrogen single bonds. And so to address this, I'm going to go back to that slide that had, and I'm going to look up the values that I need. So the nitrogen to nitrogen triple bond, that was 945 kilojoules. Per mole. And I have 1 mole of nitrogen. Hydrogen to hydrogen single bond, 436 kilojoules. 436 kilojoules per mole. And I have 3 moles of that because I have 3 of those types of bonds. And then finally, nitrogen to hydrogen single bond, 391 kilojoules per mole times 6 moles. So go back now to where I was, start adding together these values. On the reactant side, 945 plus 436 times 3 gives me a grand total of 2,253 kilojoules for the bonds that were broken. On the product side, 391 times 6 gives me 2,346 kilojoules. So delta H for the reaction is going to be 2253 minus 2346, which would be a negative 93 kilojoules. And again, the sig figs for that one, since we are subtracting, the ones place is what is maintained because the ones place is the last digit in each of those values. So we round to the ones place, which gives us our negative 93. All right. Any questions about this example? All right, let's take a look at another one then. In this one, I've got formaldehyde, CH2O, reacting with oxygen to make water and carbon dioxide. Now, before we get into anything else, we got to make sure that this thing's balanced. We've got 1 carbon, 2 hydrogens, 3 oxygens, so we're good. Okay, so what I want you to do, do an evaluation and split it up, figure out what bonds are here, what bonds are here, and what values you need to look up. And so let's take, I'll give you about 90 seconds to figure out what bonds we need to look up. And then for those of you that don't have the table handy, I'll go over to the table and let you look up the values that you need. So go ahead and take about 90 seconds, figure out what bonds are being broken, what bonds are being formed, and take it from there. Okay, so there was a bit of a trick in this one. For whatever reason, the carbon to oxygen double bond in carbon dioxide is different in its energy compared to most other carbon to oxygen bonds. I personally am not sure of the reason, but I do know that that phenomenon exists, and that's why we have a different value, 799, for carbon dioxide compared to the rest of carbon oxygen, which is usually 743. So there is a little bit of a twist in there. There's a little bit of a trick that you have to be able to reconcile in order to get the right answer here. But if you do the calculations otherwise correctly, on the reactant side, you should get 2,067 kilojoules. And on the product side, you should get 2,524 kilojoules, which means that delta H of the reaction, which is the difference of those two, is going to be negative 457 kilojoules. And this does make sense. I mean, compared to the last reaction that we had, combustion reactions are more exothermic. Combustion reactions are generally quite exothermic because we're talking about something catching on fire. And so when formaldehyde catches on fire and produces these products, this is the result, and we get a good bit of heat. And actually, for combustion reactions, is relatively low. We usually see significantly higher than this because there's a lot more carbon and hydrogen to burn.